many disciplines. And in physics, that is no different. So if you go back to calculus 1, I'm sure you would remember that if you're given speed, right, and you differentiate it once, right, you're going to get, that's going to be equal to
I gotta go now.
velocity,
Yeah.
right? You differentiate it again, you're going to get acceleration, right? So in other words, the first differential of speed gives you velocity. The second differential of speed gives you acceleration, right? So in other words, acceleration is the first derivative of velocity, right? So I'm going to show how this is applicable to us in real life. Okay? So acceleration is equal. Wait, first let me say what I've just shown. We went forward, right? We went from speed to velocity to acceleration. But what happens if you want to go the other way around? Okay, so what if you want to go from acceleration to velocity and eventually? Okay, so acceleration is equal to a change in velocity with respect to time. I'm sure you'll see that it was quite similar to what that. Okay. But it's quite similar, right? Acceleration is equal to a change in velocity with respect to time. I'm sure you will agree with me as well if I tell you that dv is equal to a dt. Am I right? Okay. So if we find the differential,
you are right if you remove that equal to there.
Right? So if we find the differential of dv, right? As we move from v to v naught, right? And we find the differential of a dt as we move from t naught or t initial to delta t. Sorry, I think it should be the other way around, right? We'll see when upon differentiating these, right? Upon integrating these two, we'll see that v minus v naught is equal to a delta t, right? What we really want to find is velocity, right? So velocity is equal to a v naught plus, because we're taking this minus, we take it over, we get v naught plus a dt. Okay? So let's look at velocity now.
Yes, before you proceed, what up there is equal to is there. You see that removed out. Another thing is that what I don't understand is what happened to the t naught?
The t naught.
T naught in the integral, lower limit t naught.
Yeah, we're trying to see how this changes.
Yes.
Right, as we move from.
Exactly, that is right. But why is it not in the system t naught? You are only placing delta t.
Yeah.
No, next step you are only placing delta t.
Yeah, well.
So you are placing delta t because you are substituting the limit, isn't it? But why are you not substituting t naught? I don't know. I'm asking you. Is it a strategy? Okay. Are you with me? Yes. Continue. I'm asking you. I don't know. Continue, madam.
Right.
Continue. You continue. It's okay.
Right. So velocity is equal to this.
Okay.
Right. So velocity, right, is equal to a change in speed. Let's replace that speed with some distance x, right, as we change in time, right? So dx is equal to dt v plus dt. Let me see if I'm correct.
v plus dt?
No, times dt. dt or delta t, right? If we take the integral of the x and integral on this side, again as we move from x to x naught, x, right? And we move over here, we move from the same t naught to some distance, some time t, right? We find that this is equal to x minus x naught, right? Is equal to x naught v naught dt plus half a delta t squared, right? If you need to work on it, this is available to you, but upon integrating this, we get this. And upon integrating this, we get this, right? So, we want to find for x. So, x is equal to x naught plus v naught dt delta t plus half a delta t squared, right? What you're looking at here, if you know anyone who does physics, these are the equations of motion, right? This is the first equation of motion, and this is the second equation of motion. With these two equations, we and scientists in general can be able to describe to you how a certain physical state or a certain system under investigation, how that system moves as time progresses, or how the rate in which it moves changes as time progresses. And this could not have been possible without calculus.
Yes, but